Hello.
आप इतना इंटरेक्ट कर सकते हैं सर? तो लाइव इन 5 मिनट्स। स्ट्रीम तो बंद कर देता हूँ। सर बोलो।
So we will be starting the SRF section presentations about 2 minutes from now.
Sounds good.
Fine, yeah. Fine from my end, yeah.
Sounds good.
Okay.
Good morning.
Kobe.
A very good morning to everyone. So today is we are in the second day of VLSI Design Conference, and this session is related to Student Research Forum, where we have 6 presentations. Okay, so we have 4 judges to evaluate the presentations. The Professor Amlan Chakrabarti from University of Kolkata, and Professor Santosh Biswas from IIT Bhilai, and Mr. Proshit Mukherjee from Qualcomm, and Dr. Balaji Jairam from Global Foundries. So thanks judges for agreeing to evaluate our presentations. So the first presentation is match line controlled content addressable memories, low power and high speed searching. It will be presented by Sheikh Wasmir Hussain from NIT Meghalaya. So let's invite Sheikh Wasmir Hussain for presentation.
Hello.
Greetings to everyone. Myself, Sheikh Hussain, will be presenting the thesis work on match-line control content addressable memory, low power, and high-speed searching. The introduction to content addressable memory followed by problems will be cited. Then the research objective to solve some of the problems will also be mentioned. Out of all the method contributions, only the first to third will be discussed in detail, followed by conclusions, future talks, and related publications. In content addressable memory, data stores are accessed based on content rather than physical location. Such access in CAN is made in a single clock cycle, therefore it produces high throughput or high speed searches. An example of the database shown here, a typical request will be to read the name and read the second name in the database starting with letter doctor instead of read the name at address 1674. Such kind of database searching are applied in network routers, lookup table management, cache memory, translation with aside buffers. Major problem associated with content addressable memory is the huge power consumption, which is more severe in non-matched line, although non-matched line ensures very high speed. As part of the research work, we categorize the research objectives into 4 CAM designs. The first one is to design low power NOR CAM. The next one is to design high-speed matchline scheme for hybrid CAM. The third one is also to design low power NOR CAM, but with major focus on reducing discharge power. The fourth objective combines all the remaining contributions, which will be the improvement on the cell level, including matchline control scheme to increase energy efficiency. The first major contribution in this thesis work is the matchline division and control scheme. A high-speed NOR matchline is divided into 2 sections, the first one here and the second section here. Based on the results in the first section, the discharge of the second section will be controlled to be eliminated so that based on mismatch filtering of the first section, huge amount of power can be saved in NOR-type CAM. This is also demonstrated clearly in the rightmost figure by showing the natural mismatch scenario. Along with matchline division and control CAM, relevant CAMs are also implemented to be legitimately compared for performance improvement. Matchline section length variation is important to determine the lowest power delay method for fixing section length for a fixed word length. As compared to MSCS and early EPPP CAM, proposed design improves energy efficiency by around 48% to 55%, although there is 11% compromise on the delay compared to the conventional CAM. Compared to state-of-the-art CAM, the proposed matchline division control CAM proves to be better in terms of energy efficiency, and also EPP turns out to be one of the best. The second contribution is the matchline control unit for hybrid CAM. As per power reduction, the strategy is quite similar to the previous step, but the delay associated with non-matchline is eliminated by using high gain overdrive comparison part here instead of the pass transistor comparison, and also on matchline also discharges only two transistors here and therefore the matchline delay is quite reduced. Compared to segmented matchline architecture and conventional CAM architecture, the matchline delay of the proposed CAM is the least, with input first speed around 88%. The third speed improvement combined with the reduction in energy has led the proposed CAM to achieve 3.36 to 2.53 better EFS delay product than the existing hybrid CAM. Compared to the state-of-the-art CAMs also, the delay reduction is quite significant, reaching up to 29% over EPP CAM, which is one of the recent CAMs. The proposed CAM also shows a minimum reduction of 47% in the energy delay product among the state-of-the-art CAM architectures. The third contribution is the two-layer matchline sensing CAM. In this design, P and N types of comparison blocks are placed in the form of the two layers so that charge minimization and charge reversal techniques can be utilized to reduce voltage strain of the matchline layer during evaluation and the pre-charge process during pre-charge phase. Matchline delay is also quite improved in this particular CAM because unlike the existing work, the delay won't be dependent on the discharge behavior of the layers of the segment, but only it will pick up the charge at M layer and then will pass on through the transmission gateways included in the matchline pre-charge sensing block. The voltage transmission and pre-charge sensor schedule is shown in this table. Master slab matchline design also has huge amount of voltage scheduling, but the problem associated with the 4 segments per row, which leads to overhead charges. The same type of issue is also seen in local global mapline architecture. In the proposed two-layer mapline sensing scheme, there is the low voltage discharge in evaluation and lower voltage discharge in the precharge phase. This is shown in V3 by considering V equal to 1 volt. Because only two segments, because the proposed design limits the segments to only 2 layers, the voltage reduction does not cause much overhead in the charge. This operational phases in the binding diagram also demonstrate the voltage minimization and the resource strategy to solve a much amount of the precise power in VLMLS scan. Precise power of the proposed design reduces at the rate of 17% to 23% as supply voltage is scaled from the highest node, that is 1.2, to lowest node, that is 0.8 volts. An approximate reduction of 25% is ensured over one of the recent GAN, that is GPMLS GAN, and a maximum precise power reduction is observed against master slot mapline design, which is around 82%. Because the reduction in precise power is quite significant, contribution of precise power to PML is lesser, which is around 30%, but in the conventional GAN, it is around 49%, so there is a huge difference in the contribution. The remaining contributions are summarized in this table. In all these designs, the same level design schemes are made mostly for reducing transistor count, area, and improving speed, whereas the mapline control and design schemes are made for reducing power and improving energy efficiency. As part of the conclusion, we can summarize as no power chain design for NOR has been implemented with a slight compromise on delay. High-speed scheme of hybrid mapline scheme has also been designed, which shows the huge reductions in delay. A two-layer mapline scheme designed for reducing huge amount of precise power using roasting and charge minimization. Total mapline power in this particular work reduces by around 28 to 59%. As part of the future work, the next generation designers are encouraged to employ next CMOS, post-CMOS, and emerging technologies to implement non-volatile GANs and also to implement mapline control and predictive circuits. The remaining details of the process can be seen from this list with some other related reference continues till here.
Hello. Judges can ask questions directly. Thanks, Sek, for your presentation.
Yeah.
Judges can ask questions directly.
Sure, Professor Vishnu. Yeah. Hi, Sheikh. This is Balaji here, and thank you very much for your presentation. So I have a question. So you're saying tape out is part of future scope. So I was just trying to understand the comparison results that you have. So is that based on simulation for you and hardware results for the rest of the prior arts? Sheikh, you need to unmute yourself. We're not able to hear you.
Is it audible now, sir?
Yeah.
Okay. We are actually in the process of tape out, but that technology is different. So that means that is SCL 180 nanometer. But the previous work of my thesis till now, we have implemented using 45 nanometer technology. So what we do is all this relevant work also we pick up the match line structure or the prerequisite structure from the paper, and this comparison is made by purely implementing by us and in post-layout simulation in the same environment.
Okay, so when you're saying the prior art is also simulated, meaning you redo that and you're checking it against yours. Okay, so everything is simulation based.
Yes.
Okay, thank you. One other question, the follow-up question is, you mentioned that for your control scheme, you have a higher gate overdrive in order to improve the speed.
Yes, yes.
So does this involve some design complexity because you need a higher overline voltage or something?
No. Thank you for that question. Actually, what happens is in the previous state of the art, in most of the game, they use some comparison circuit that have pass transistor logic structure. So in the pass transistor logic structure, the main problem was degradation in voltage issue, especially while trying to pass logic 1. So in our design, what we do is the cell level improvement is that we employ the dynamic NAND or NOR, dynamic XOR, NAND or NOR structure, so that while passing that one, logic 1, there won't be voltage drop. So that particular transistor which are responsible for passing logic 1 or logic 0, it will pass sufficiently. That is the
Okay.
reason why we use the term gate overdrive.
Okay. Okay. So it's not a pass gate based, it's conventional logic gate based. So there is no voltage drop because of that. Okay. I get it now.
Conventional dynamic, and
Yeah.
only in the comparison part.
Okay. Yeah. Thank you. I think that's all from my end, Professor Bishnu.
Thanks, Dr. Balaji. Is there any other questions from the audience? If not, I'll move to the second presentation. The second presentation is investigation of saturation phenomena and self-healing induced TC variation in SOI FinFET by Sasank Kulcher from IIT Roorkee. Please, let's invite Sasank for presentation.
Thank you, sir.
First of all, I would like to thank you to attend the online presentation of our work. My name is Shashank Banchor and I am a research scholar under the supervision of Professor Anand Bulusu in Electronics and Communication Engineering Department at IIT Roorkee. Our research topic is investigation of saturation phenomena and self-heating induced JTC variation in SOI FinFET. So before giving you some facts and figures, I would like to give you some overview of our work. Since FinFET is an industry adopted and very popular device because of its excellent performance in comparison to the planar MOSFET. However, it is a general conception that the physical phenomena in FinFET would be similar to the planar MOSFET. However, in our work, we have showed that the unique structure of FinFET, including the drain extension region, makes it possible to have some different kind of physical phenomena to govern the electrical characteristics. So first of all, we analyzed the saturation phenomena in output characteristics of FinFET device and discussed various findings. We have also proposed a model to estimate the drain saturation voltage. Since self-heating effect is also an important and critical concern in SOI FinFET devices, and it is mainly dominated in the saturation region. So we have also explored this phenomena. After that, we have proposed some models and methodology to design a reliable analog circuit, about which we will discuss in this presentation. So this is the complete outline of our work. Since technology scaling improves the device performance in terms of speed, power consumption, cost, etc. However, there are several challenges which also comes with the scaling, such as short-term effect. So to overcome these limits, there are several techniques such as multi-gate devices, strand silicon, high-K insulators, etc. And FinFET is one of them. FinFET is a thin FinFET body wrapped by the gate. It can be either double gate device or tri-gate device based on the thickness of the top gate. Top oxide. So this is the structure of the FinFET device. It has the source region, drain region, box, substrate region, and this is the pin of the device. So these are the several advantages of FinFET. It has better electrostatic gate controllability, reduced leakage current, improved short-chain effect immunity, etc. So this is the 2D schematic of a FinFET device. There is a constant doping in source, drain, and channel region. However, there is a Gaussian doping in the source and drain extension region. These are the dimensions of the device which we have used. We have used 11.7 nanometers, 16 nanometer, 20 nanometer gate length, and other device dimensions are also listed here. So in this work, we have observed that the physical phenomena in FinFET is not similar to the planar MOSFET. We have also observed that the behavior of output resistance in FinFET is different in comparison to the planar MOSFET. So this is the output characteristics of FinFET device, and here it is the G function. G function is a technique to estimate the drain saturation voltage. So based on the G function technique, we have extracted the saturation voltage for different technology nodes. Here we can see that the value of VD set at 14 nanometer SOI FinFET, 11.7 nanometer, 16 nanometer, and 20 nanometer FinFET devices. We have also extracted the VDSAT values for different underlap and overlap gate lengths. So we have observed that the VDSAT exhibits linear relationship with VGS for higher values. It is also found that this linear relationship of VDSAT becomes more accurate with the technology scaling. It is very useful for analog circuit design viewpoint. So we have also observed the behavior of electron density and electron velocity and their product at the surface of the fin and at mid of the fin. And in our analysis, we have observed that the product of the electron density and electron velocity gets reduces after a certain VDSAT at the junction of the channel and drain extension region. So based on this analysis, we have proposed a semi-empirical model of VDSAT, which is given here. We have also analyzed the behavior of analog performance parameters. Here can be seen we can see the behavior of transconductance, output resistance, and intrinsic gain for FinFET devices and for planar devices. We can see that the transconductance of the FinFET is higher than the planar MOSFET, and it can also be observed that the output resistance of FinFET is not similar to the planar MOSFET, because in planar MOSFET after a certain value of VDSAT, output resistance gets reduces, while in FinFET it is continuously increasing nature. We have also the behavior of intrinsic gain in FinFET has continuously increasing nature with VDS, while in planar MOSFET it kept constant throughout the VDSAT values. We also observed the behavior of gate to drain capacitance and gate to source capacitances for different VDS and VGS values, and we observed that the behavior of capacitances is also different in FinFET devices, because in planar devices after a certain VDS value, gate to source capacitance kept constant, while in FinFET device it is decreasing after a certain value. So since self-heating effect is also a critical concern in FinFET devices due to its confined structure and the box layer beneath the silicon layer. Here we can see the thermal profile of the FinFET device. Here we can observe a hot spot region at the junction of drain extension and drain region. So due to the additional increase in the temperature, carrier velocity and threshold voltage decreases, and due to that a serious device performance degradation and reliability problem exists in the device. Here we can observe that drive current decreases with the self-heating effect. So here we have shown the 3D schematic of our device and our calibration of TCAT models with experimental data, and these are the dimensions of the device. Here we can observe that the profile of lattice temperature and current temperature at different region of the device. Here we can observe that peak of the maximum. Here we can observe that the peak of the lattice temperature exists at the junction of drain extension region and drain region, while the peak of the carrier temperature exists at the junction of channel and drain extension region. Here we can see that the current degradation is much higher at higher gate to source voltages. We have observed that a 16% current degradation and 82 Kelvin temperature rise in the device at higher values of VGS, while it is negligible for less VGS values. Here we have also shown the power temperature characteristics for different values of VGS. Here we have shown the behavior of zero temperature coefficient for isothermal condition and for self-heating condition. Since ZTC is a point at which the drain current is temperature independent. As we know that as we increase the temperature, then threshold voltage gets reduced. Due to that, current increases. Similarly, as we increase the temperature, then mobility also decreases. Due to that, current reduces. So due to the mutual cancellation of both the effects, point exists at the transfer characteristics at which the drain current is temperature independent, which is called ZTC value. This ZTC value gets reduces with the self-heating effect. So to analyze this phenomena, we have observed the behavior of threshold voltage and saturation velocity, and we have observed that both the parameters get reduces with the self-heating effect. So based on this analysis, we have proposed a model to estimate the zero temperature coefficient. Since the JTC drift, which is the difference of JTC values without self-heating and with self-heating, is an undesirable effect, which is mainly pronounced in the pronounced at the higher values of VDS values. So to minimize this JTC drift, we have explored the device parameter variability and found that a higher drainage sensor region and higher fin width can minimize the JTC drift. So based on this analysis, we have designed an analog circuit and found that a stable circuit performance can be achieved with biasing the circuit at JTC values. So this is the conclusion of our work. Our work mainly focuses on the challenges of analog circuit design issue and its solution with knowledge of latest operation regime. So we have analyzed various physical phenomena such as saturation phenomena, self-heating effect, etc. for the FinFET device and propose a model's methodology to design a reliable analog circuit. So this is the list of publication and these are references. Thank you.
Yeah. Hi, Shashank. This is Balaji here again.
Shashank, please, questions. Yeah.
Yeah. Thank you, Professor Vishnu. So I have a question. So first of all, thank you very much for the presentation. It was very good. The question is, what is a typical time constant that you would observe for a FinFET for self-heating?
Sir, actually, we only analyze the static behavior of the FinFET. We have not analyzed the parasitic capacitance. Thermal capacitance. We only observe the thermal resistances.
Okay. Okay.
But the thermal constant is around 1 nanosecond because the thermal capacitance of the FinFET is around 1 gigahertz, so that the total time constant would be around 1 to 2 nanoseconds.
Okay. Yeah. Thank you. So the second question I have is on the ZTC that you have characterized, right? So I understand that the characterization of zero temperature coefficient is good for biasing circuits, but I was just wondering how good that is for a typical analog circuit where you are using it as an amplifier and where you have your gate voltage shifting by say 50 or 60 millivolts, and your ZTC already is of the order of say a few tens of millivolts. So I'm not able to correlate well as to why that characterization is important.
Yeah, because yes, question is right. The ZTC shifting is around 50 millivolts, but it is a large part of overdrive voltage. So we believe that. So we believe that this shifting of ZTC can significantly affect the circuit performance. So we analyze this impact, and as the self-heating will be more in the device, then this ZTC shift will be larger. So we propose a model to estimate the ZTC point for both the isothermal condition and self-heating condition.
Okay. Yeah. Thank you. I'm done, Professor Vishnu.
Thanks, Dr. Balaji, for the questions. Thanks, Shashank, for your presentation. So the next presentation, the title of the presentation is Test and Characterization of Analog Circuits by Analyzing Transient Response Using Statistical and Machine Learning Approach by Supriyo Srimani from IIEST Sripur. Let's invite Supriyo for the presentation.
Everyone, myself Supriyo Srimani, a research scholar of Indian Institute of Engineering, Science and Technology, Shibpur. Today, I am going to talk about my thesis work on test and characterization of analog circuits by analyzing transient responses using statistical and machine learning approach under the supervision of Professor Hafizur Rahman. This will be the outline of my talk. First, I will discuss about the analog circuit testing and its challenges. Next, I will briefly discuss about my motivation behind this work. The working chapters are divided into 4 groups, which I shall discuss in the presentation as the presentation progresses. Finally, I will conclude after discussing the advantage of this methodology. We are all aware that analog circuit deals with continuous signals, which leads to nonlinearities. Large varieties of analog circuit exist in today's technology like filters, amplifiers, and many more, which operate in a wide range of frequencies. So it is very difficult for a test engineer to develop a testing technique for these varieties of circuits. Furthermore, digital circuits possesses a few typical faults like stuck at 1, stuck at 0. However, in case of analog faults, there are no generally accepted fault models. Also, transistor scaling over the past few decades have ensured a steady decrease in manufacturing cost per transistor. However, the test cost per transistor has not decreased with the process advancement. As I continue for the motivation, the real world, most of the components present are in analog in nature. Also, the demand to test those components are quite high and is challenging because of their operation. Analog circuit do not have an acceptance or rejected criteria defined by threshold. Tolerance of circuit components and their signal noise increase the difficulty of analog testing. Fault diagnosis of analog component could lead increase in time to market. Reduction of the hardware cost and the testing time of the conventional performance measurement technique will drastically reduce the test cost. This slide provides an overview of my work. First, I have worked on a test simile which is used to test the algorithms and applied as an input irrespective of the circuit. I have worked on mainly two problems. One is fault detection and another one is fault diagnosis. Fault detection part has been addressed with a statistical learning where I have worked on two mainly problems, namely as parametric fault detection using Bhattacharya measure, and another one is a parametric fault detection using Komolov similar test using the Mars model. The diagnosis part has been addressed by machine learning algorithm as each component has different effect on the circuit responses. Finally, I have worked on indirect testing of functional parameters to increase the time to market. I have tested the algorithms on 5 test circuits, namely as 4-op-amp biquad high-pass filter, continuous time low-pass state variable filter, second-order silent band-pass filter, cascade amplifier, and two-stage amplifier. But due to time constraint, I will show the results of 1 or 2 circuits for each algorithm to show the effectiveness of the algorithm. All the test circuits has been designed in Cadence Virtuoso using UMC 180 nanometer technology, and the testing algorithms are implemented in MATLAB for validation. All the circuits are pre-assumed to be stable in PVT variation. The testing algorithms are also validated by hardware result of one circuit, that is second-order silent bandpass filter developed using practical IC TLB2762CD by Texas Instrument. Test stimulus is an important parameter for higher test coverage. Designing an optimal pattern of testing should meet the necessary specification like detection of every fault, pre-assumed fault in the fault model, simplicity of generation, and shorter test time. Keeping this in mind, a pseudo-random test-based test simile has been used to excite the circuit under test. The DAC convert LFSR generates pseudo-random bit sequences to an analog signal. For a random input signal in T, shown in the figure, the output of an analog circuit is a new random signal YT, which can be considered as a linear transformation of the input random signal by the analog CUT. In this work, the random analog simultaneity is generated by a 12-state internally XORed LFSR followed by a DAC. The power of the signal is fixed based on the allowable range of the PDK and the CUT. There are some advantages of using pseudo-random signal, like a pseudo-random signal has a property of being space spectrum, which means that the spectrum power of the pseudo-random signal is spread over wide range of frequencies. A pseudo-random signal will excite the CUT with large number of frequencies simultaneously with varying amplitude levels, and thus will increase the testing to be performed through outputs of the CUT. In the first working chapter, parametric fault detection of analog circuit based on Bhattacharya measure is discussed, where the component tolerance is taken as 5% from the terminal. The Bhattacharya distance in the first equation and the angle in the second equation between the fault-free and the faulty instances are taken as the statistical distance. The P1 and the P0 denote the probability density function of the output response of the faulty and fault-free circuit respectively. The theory behind is that whenever the component, one or more component of the CUT varies, the probability density function of the CUT is also varies. The probability density function has been calculated by a non-Gaussian autoregressive model given in the equation 3. The model parameter is estimated by solving the Wheeler-Walker equation and the solution of equation 5 and 4. The two test circuits has shown with the variation of the probability density function for the component fault, resistance R4 in the filter and the width variation in the amplifier circuit. Considering 5% component tolerance in all the components, the accuracy of the fault detection algorithm is clearly higher than the functional testing, where gain and bandwidth is taken as the functional parameter shown in the table. In the next work, fault detection has been carried out by case test estimating tolerance by Mars model. In the previous work, the component tolerance is taken as plus minus 5% for all the components. However, the fault-free range of circuit component should be determined from the specification, since the dependencies of the performance parameters on different circuit components are different. So in this work, a mapping function is derived using Mars model, which helps the performance metric with the circuit component. From the mapping function, the tolerance of individual component has been found. Fault detection has been carried out from the empirical cumulative distribution function of the output of the card by applying the pseudo-random signal at the input. To illustrate the algorithm, 4 performance parameters has been considered for silent bandpass filter. The considered performance parameters are gain, bandwidth, Y21 and Z11. The graph shows the nonlinear behavior of the parameters due to circuit parameter variation. The range of circuit component for ±5% tolerance ranges of these performance matrices are then found by this equation for all the circuit components. This figure represents the ECDF of the random output of the COT for nominal condition and faulty cases. The second figure introduced the ECDF of the nominal condition of the cascade amplifier of the op-amp injected fault in the width of the MOSFET, and the table shows the accuracy with the previous work. Experimentally rejected test result of Salenki bandpass filter for fault is taken for resistance and capacitance only. This figure shows an experimental result for few single as well as multiple detected faults. In the next work, fault diagnosis is achieved by machine learning algorithm using wavelet transform as a preprocessor. From the output response of the circuit excited with pseudo-random signal has been obtained. 10 level of wavelet multi-resolution analysis along with the 16 distinct feature extraction processes is used to generate the feature set. Probabilistic principal component analysis has been used to reduce the size of the dataset. The classifier is then trained with the selected features. If the fault coverage or the accuracy is deficient, the next step adds the proposed boosting technique by combining the base classifier. The boosting technique can be continued until the desired fault coverage is achieved. The middle figure shows the variation of the bandwidth and the central frequency with the variation of the circuit component in the left hand side for ±50% of the component variation. The figure shows that ±50% component variation changes the central frequency for the component R4 and R5 very little, as they are forming a groups, but the bandwidth depends on all the passive components significantly. For this reason, all the passive components are taken as faulty in this work. To increase the fault coverage, adaptive boosting algorithm combines the series of base classifier, and the result is assigned to the corresponding class by the voting mechanism shown in the figure. The confusion matrix shows the increase in the diagnosis accuracy where the base classifiers are artificial neural network and support vector machine with their optimum internal parameters. The table shows the comparison result where it clearly shows that if the ambiguous group were not considered, then the accuracy is similar to other algorithms, but in presence of the algorithm ambiguous groups, the accuracy is also compatible. The next work is on the indirect functional testing using neural network. In practice, analog and mixed signal circuit is assessed by quantifying its specification. If one of the specs is out of the limit specified, the card is treated as faulty. However, analog circuit comprises of different performance parameters which require different input to test as well as different costly equipments. In this work, a test procedure for faster production testing of analog circuit has been demonstrated. For validation of the algorithm, and two-stage op-amp is taken, and the different performance parameter and mismatch parameter has been taken to replicate the scenario of the silicon data. The functional parameter selected for validation of the amplifier along with the nominal value is given in the second table. The x-axis of the plot denotes the value of the functional parameter generated by direct simulation, while the y-axis represented the predicted value from the proposed technique of the corresponding functional parameter. The ideal correlation amongst the predicted and the simulated specification are highlighted by a perfect 45-degree plot. As for the conclusion, to summarize, prime advantage of this method is that it requires only the output voltage for a given random input voltage. Due to the use of the pseudo-random signal, the design complexity reduces a lot. The overhead of the test cost and the test time of the functional testing can be reduced by indirect testing. As for the future work, the testing of the gigahertz signal is my main focus, but the circuit internal capacitance will play a major role, and circuits where the output response is not varying with time and frequency. These are the publications related to this thesis. These are the other publications in my PhD tenure. These are the few references. Thank you.
Yeah, thank you, Sir Supriyo. So I am Santosh, and I have a couple of questions. So thank you for the nice presentation. So you were saying that you are using artificial intelligence based schemes. You are using a DAC and ATC based pairing to the testing of analog circuits. So it seems that the area overhead or the resource overhead will be too high. As per my understanding, because analog circuits generally have only a few tens of transistors. So if you want to test an analog circuit using an ATC DAC pair, or you want to use machine learning based techniques, so will it not increase the area overhead of the resources too high, rather than going by a traditional approach of using analog instrument for the testing? Your comments.
Hello, sir. Am I audible?
Yes.
Yeah. Okay, sir. The first question is the area. Actually, for modern ATE architectures, the pseudo-random signal can be generated. And for modern SOCs, internal LFSRs are also there. For modern digital IC testing, we can use that LFSR for generate the pseudo-random input stimuli. And we are not using an ADC for converting the analog to digital part. We are only using a LFSR for pseudo-random input stimuli and converting that pseudo-random stimuli through a DAC to a pseudo-random and analog stimuli. So, according to your question, the area over it is high if we integrate the total architecture in a single BIST architecture, but we are not implementing the BIST architecture. We are using the property of the ATE to generate the input stimuli and test the circuits.
Okay, and how do you implement these AI-based techniques?
Sorry, sir, I couldn't hear you.
And you have also said something about artificial intelligence or machine learning kind of.
Yes, so machine learning approaches are used for batch processing. For a huge number of circuit component testing, it is the time to market is very much low for a test of 1,000 ICs. So we are using that machine learning approach to test those 1,000 ICs as quick as possible, so that the consumer can get as fast as low as time as possible to test those ICs. So that's where the machine learning approaches comes, whether you can just directly judge whether an IC is faulty or not, or component can be diagnosed with respect to from its output responses. And in the last work, as you have said, from the functional instrument parameter, suppose you have 1,000 IC and you are testing each of them individually, it will take a long time. So for a machine learning approaches for indirect functional testing, we are testing those 1,000 ICs with a single fraction of time through machine learning approaches. That will increase the time to market.
Yeah, thank you. I mean, in the interest of time, we can conclude here, and thank you very much.
Okay, thank you, sir.
There is a question from audience. Does the proposed method enough to take care of reliability changes later in the lifetime, say after 10 years?
Okay, so we haven't checked the reliability issues, but we are already focusing on the soft faults. We are not considered the hard fault. So in thesis, we have only considered the soft fault where the circuit component varies a little much from their tolerance limit, and we have checked whether the circuit will be faulty or not. The reliability has not been focused in the thesis work.
Okay. Thanks, Supriyo, for your presentation, and thanks, Professor Santosh, for your questions and the audience. Okay, thanks. So the next presentation is estimation of random local threshold voltage variability using on-chip configurable ring oscillator. It will be presented by Purvi Jain, IIT Roorkee.
To give a presentation on estimation of random local threshold voltage variability using on-chip configurable ring oscillators. This is the outline of my presentation. As transistor density increases inside a chip with each technology node, the performance of a chip improves, but it also brings about the nanoscale effects, the reliability issues, and the issue of random local process variability has become a serious concern for the circuit designers. So a great attention is needed towards the increased variability of process variability. In older technology nodes, the large guard bands is used to reduce the process variations, but it results in the suboptimality of the design. To avoid large guard bands, efficient process monitors have been employed in the design, which enable us to rectify the SPICE model file and reduce the power dissipation of the chip by using the adaptive body biasing techniques. So in the conventional techniques, NMOS pass-based transistor ring oscillators has been used to extract the threshold voltage information. But in this case, for each DUT, a single ring oscillator is used, so it results in the large area overhead for estimating within die threshold voltage variation. So the requirement is to have the area efficient, moreover the reconfigurable process monitor along with the immune to local supply variations and can predict both the mismatch and the absolute value of the threshold voltage. So the basic idea for the threshold voltage measurement is shown. It depends upon the switch conditions. When the switch is closed, the node voltage is set to VDD, whereas in another case, when the switch is open, the node voltage is set to VDD minus VTH, and the input to output delay is measured under the two different conditions when the node voltage switch from VDD to VDD minus VTH, and this difference in the delay enable us to extract the threshold voltage impact of this DUT. So the threshold voltage measurement cell consists of the dummy structure which is used to solve the unequal loading problem, and the details of this can be found out on a paper which is mentioned here. But the input to output delay is very small and it is difficult to take out from the test chip, so it has been cascaded in the form of the ring oscillators as shown here. So in order to estimate the threshold voltage impact of this NTUT2, the time period of the ring oscillator is measured under the two different conditions where the control signal is changed from 0 to 1, and taking the difference enable us to estimate threshold voltage of this NTUT2 along with the inverter I1 NMOS transistors. So the log normal based model has been used and which enable us to extract the mismatch in the threshold voltage variation where K1 is the fitting parameter constant, and this parameter can be observed from the chip. So as it is can be seen that the model and the simulation results are closely along with each other and the maximum difference is found to be less than 2%. This is the test chip design and the microchip graph of the proposed design, and the corresponding measurement setup is shown here. Some of the measurement results where the 300 DUTs have been used for the measurement, and the delta T measurement. Delta T graph follows the log normal distribution, and the extracted threshold voltage variation forms the Gaussian in nature, which is in according with the literature survey results. And it has been found that the measured results are in closely agreement with the simulation results for the mismatch in the threshold voltage variation. And in order to show the measurement accuracy of delta T, a single DUT is measured in 10 different ways, and the maximum error is found to be less than 2 picoseconds in the delta T measurement. So the comparison technique shows that the proposed technique has a cell reconfigurable feature, and the impact of local supply variation and systematic variation is less in the proposed case, and leakage current is also less. Now the threshold voltage will be estimated using the duty cycle of a ring oscillator instead of a period of a ring oscillator. So this high frequency signal, when come out of the chip using the conventional divider, results in the equal duty cycle, which causes the loss of information, whereas subsampling technique allows to preserve the unequal duty cycle. So the subsampling technique is based on the D flip-flop, and it has been observed that this subsampling clock, when using the external clock generator, is limited by the input-output pad frequency. Whereas in conventional techniques, PLL is used, results in high accuracy, but largely increases the on-chip area. So the proposed TVMC-based RRO structure is used to generate the high-frequency signal, which extracts the information of the threshold voltage information, and the subsampling clock is generated using another TVMC-based RRO using the different control signals. And the subsample signal can be extracted using this formula. Then, it has been observed that the individual rise delay of the TVMC stage constitutes of the negative part of the duty cycle, that is the T off, and similarly the fall delay of the TVMC stages consists of the on part of the duty cycle. So any change in the threshold voltage drop due to the DUT causes to change the off part of the duty cycle. Similarly, if any change is there in the threshold voltage of the PPAS DUT, it causes a change in the fall delay, and similarly on part of the duty cycle changes. So from the equations we see that, and the model equations, that the mismatch in the threshold voltage can be observed by the change in the difference of the duty cycle. And this plot shows the measurement from the oscilloscope, that is from the Teledyne Leclerc oscilloscope. The D and the clock signals have the 50% duty cycle, whereas the low frequency subsample has 38% duty signal. This is the sum of the measured results, and it shows that the threshold voltage mismatch is Gaussian in nature, and it is according to the literature survey results. Now, in order to show the measured difference of the negative duty cycle across different delta T, so as the delta T increases from 10 to 60 picoseconds, the error in the delay measurement is 2.1, whereas it increases to 7.8 and 130 picoseconds. So using the idea of random process variation, it generally allows to have the accurate measurement duty cycle, and it saves the silicon area up to 13.5 times compared to PLL. But in these structures, it is observed that the local load variation of the duty comes into picture for the duty characterization. So there is a need to design a structure in which it is independent of the local load variation, and this is done by the large capacitor, approximately approximately 2 picofarad, which shields a local variation of the DUT. So this is based on the concept where the normal ring oscillator has been used and the supply of RRO is set to VDD in one case, in another case it is set to VDD minus VDD. Then taking the difference of these two time periods enable us to extract the impact of threshold voltage of the DUT. So it has been observed that when this ring oscillator oscillates, this supply node has a noise variation of around 10 millivolt. So what is the solution to stabilize this noise? So decoupling capacitor has been used, which shows that around 20 picofarad capacitor for 31 inverter stage RO, the noise reduces to 0.1 millivolt. But it has been seen that as the capacitor value increases, the noise voltage reduces, but at the same time, the area of the capacitor on the chip increases. So what is the solution so as to have the optimized area as well as reduce noise voltage sensitivity? So in this case, instead of driving the complete n inverter stages, a single inverter stage is driven while the rest of the inverter stages receive the power supply from VDD, and the same concept of the difference measurement of EVDD and VDD minus VTH is used. And using the exponential model, the threshold voltage mismatch can be obtained using this equation where Sn is the sensitivity of the threshold voltage variation to the supply node RO variation. So it has been observed that the local load variation contributes to around 78%, and with the help of decoupling capacitor, it has been shielded for the accurate DUT estimation. Now, it was not possible to fabricate the chip in the lower technology nodes. It was fabricated in 130 nanometers. So simulation result has been performed, which shows that the spread of this long delta by delta not increases as the technology reduces from 130 to 40 nanometer. And this impact of process variation is really a serious concern in lower technology nodes. This is the setup and the chip diagram, the corresponding diagram and the measured results, which shows the Gaussian nature of the threshold voltage variation. So the application of the process monitor is shown here. The chips are discarded basically because though it is a high frequency region, but due to large leakage, it is discarded. Then in the low leakage region, there is a low frequency in this. Both the cases, it affects the yield, performance, and the power specification of the chip. So the process monitor basically estimate the process condition, then using the controller allows to modulate the threshold voltage so as to increase the operation, reduce power, and increase the yield. So this is a system whose timing frequency requirement is reference clock, which is decided by the critical path, and the TVMC based RRO is used as a tunable circuit and which mimics the critical path. So the comparator is used to compare the reference clock and the RC out. If it is found to be slower, then the target system failed to meet timing requirement. So the body biasing technique is used to have a close relation with the reference clock. This is the tracking of the replica critical path, the actual critical path, and 1.2 and 0.8 volt, which shows that the proposed process monitor can be used for tracking the critical path. And this simulation result shows that in the last case, the 3.2 is the operating frequency requirement, and this timing is violated. So after the biasing, the delay has met the timing requirement. So the conclusion is that the threshold voltage variability has been measured using the period duty cycle of the ring oscillator, and the application has been used in the body biasing control techniques to improve the yield, performance, and the power specification of the chip. These are the publications. Thank you.
Yeah. So thanks,
Any
Purvi,
questions?
for this excellent presentation.
Thank you, sir.
So I have a couple of questions, Purvi, here. First of all, is that it would be very interesting to see that how the limits of the variability, okay, versus the number of stages of the ring oscillator. Okay, we can do a sort of comparison, right? Because the variability limits, okay, so that you need to take care of. That means your design is is capable of of estimating the limits in the variability, right?
Right.
So that I didn't get directly in your presentation. Might be it is there in your detailed paper. So
Yes.
so I wish to get some answer on that point.
Because,
And my
yeah, like I would like to add here, sir, like the simulations have been performed across different stages, and it was found that due to the different nature of the technique, like we are measuring the impact of the threshold voltage of the DUT, and the method or the proposed technique is based on the difference of the measurement technique. So it cancels out the impact of the rest of the DUT. So only the single DUT is under observance. So it is seen that only the change in
yeah, fine. So you tell so when you tell the slow frequency and your frequency signal, high frequency signal. So what are the bounds you are actually trying to go through, right? What are your bounds in that?
Like up to 30, 31 inverter stages, the change in the delay was very less.
So what I want to see, I think you are also trying. That means you are also looking in that. So what is your basic model in terms of the various parameters in the variability, some of the thresholds in the variability, vis-a-vis the design parameters of your RO oscillator? Okay.
Yes.
So that would have been that might be good. And my second question is that means when you are trying to go in the reconfigurable part of the RO, right?
Yes.
So what is your exact pitch in terms of reconfigurability?
By reconfigurability here means that the duty can be reconfigured. Like at each time, only one duty can be selected. So by just changing the configuration of the status vector of the signal, then you can select the another signal in the same RO structure. Because in the earlier conventional techniques, what was happening for measuring the impact of threshold voltage variation of the single duty, it requires one RO. So to measure within die variation, suppose like thousands of duties are needed. So it requires thousands of ROs. So it requires a lot of area.
Yeah, did you estimated the power also for this? That means how does your power requirement gets extended for this?
Like power requirement could not be measured because from the chip there are many structures were there, so there was not dedicated power supply line. So yeah, the core supply was common. That's why.
Okay, so the trade-offs trade-offs were not that means not very well. That means you cannot estimate the trade-offs very accurately, right? Here.
Like trade-offs, like we can measure like the trade-off was there between the supply noise and the area of the capacitor in one of the technique. So what was happening to incorporate the supply noise to less than 0.1 millivolt, the decoupling capacitor has been used. So it was seen that if 20 picofarad capacitor is used, it was occupying more area on the chip. So we have found out a technique such that the capacitor can be reduced as well as capacitor area can be reduced, and moreover the supply noise can also be maintained up to 0.1 millivolt. So the 2 picofarad capacitor has been used, which has reduced the approximately area of 10 times, and so that's why we have proposed the local variation insensitive process detector. Yeah.
Fine. Thanks, Purvi. Due to the interest of time, I'm not stretching further, but good research. Okay. Thanks once again. Yeah.
Okay. Thank you, sir.
Yeah.
There was a question from audience. Where is the configurability introduced in the architecture?
Like configurability has been introduced in the structure where has been shown that TVMC cell, the threshold voltage measurement cell. So a duty is used in a single RO structure. Suppose you are having n duties. So in order to select one duty at a time, we are having a configuration status vector. So that's why the configurability has introduced here in order to select the duties. Hope
So
I am clear.
There is another question. Are you using differential measurement for VT check?
Yes, like the difference measurement is like in one case, when the duty impact is not there, the node voltage is set to VDD. Whereas in another case, the configuration status vector has been set such that the impact of duty is observed, which is set to VDD minus VTH. Then taking the difference of delay under these two conditions helps in measuring the impact of threshold voltage of the duty from the measured delay.
Yeah, thanks, Purvi. For the interest of time, I cannot ask you more questions. Okay, thanks, Professor Amlan, for your questions. Okay, next we'll move to the next presentation. This is the title of the presentation is Nonlinear Modeling and Analysis of Power Delivery Network. It will be presented by Bijendra Kumar Sharma from IIT Mandi. Let's invite Bijendra for the presentation.
At IIT Mandi. The title of my presentation is Design and Analysis of Power Delivery Network. This is a typical block diagram of an AMS system, that is analog and mixed-signal system. It consists of a power management circuitry and a digital system and analog system, a mixture of both analog and digital system, that is called
These are the analog and digital I/O drivers that are responsible to communicate with the external world. The power management unit consists of an AC to DC rectifier stage, a DC to DC buck converter, and power delivery network. The role of the power management unit is to provide a constant DC voltage to the analog and mixed signal system. However, in practice, it has some AC fluctuations. These fluctuations can deteriorate the output of analog system as well as digital circuits. The analog circuit output can be deteriorated in terms of gain, phase, UGW, location of poles and zeros, and hence the overall stability of the system may be affected. In case of digital system, the output of the digital system can be affected in terms of setup and hold time violations, noise margin, bit error rate, and jitter. In this presentation, first I will show the nonlinear analysis of PDM using the Volterra series. The proposed nonlinear analysis can be useful in the designing of a robust PDM so that the minimum fluctuations are presented at the supply node. Next, I will discuss the two proposed methods for the analysis of typical SI matrices of an AMS system in the presence of power supply noise. The typical signal integrity matrices are gain, phase, unity gain bandwidth, input-output impedance, location of poles and zeros, and power supply induced jitter. These methods are block approach indefinite admittance matrix and estimation by inspection method. Both the methods are based on indefinite admittance matrices. After that, I will discuss the nonlinear analysis of closed-loop buck converter in the presence of PSN using the inspection-based method and Volterra series. Before proceeding to the actual analysis, first I will give a brief introduction on the Volterra series. Volterra series provides a structured and convenient mathematical relationship between the input and output response of a nonlinear system. Here, xt is the input and yt is the output. The yt is a combination of first order Volterra kernel, second order Volterra kernel, and the higher order kernels. These Volterra kernels are calculated using the convolution of input with the impulse response of the system. Now coming to the analysis of distortion of power delivery network, this is a schematic diagram of a DC to DC buck converter including the board, package, and load impedance. These S parameters of a practical board and package are extracted using the 3D EM solver tool. For the analysis purpose, this power MOSFET is replaced by its nonlinear resistance as it is operated in the linear region. The S parameter converter includes equivalent T network as shown in this figure. Here, L and C and the load are assumed as ideal element, and these are not included in the nonlinear analysis. By applying the Volterra series on this circuit, we can derive the fundamental response, second order harmonic, third order harmonic, and harmonic distortion quantities and intercept points. For the analysis purpose, the pulse width modulated signal has a constant duty cycle and the small perturbation present at the source terminal of the power MOSFET. Here, we consider three different cases for the purpose of validation. In the first case, an open loop buck converter is analyzed and its nonlinear response and distortions are derived. In case 2, the nonlinear quantities of a buck converter with the equivalent model of PDN are derived. In the third case, we included the practical effects of board and packages for the analysis purpose. The closed form expression for all three cases are written in this table. Here, beta 1, beta 2, beta 3, and beta 4 are the function of mu n, COX, W, L, and parasitic of board and packages. Here, alpha 1, alpha 2, and alpha 3 and Z1 are the function of Z parameters of PDN. So, validating the proposed method, a 50 Hz sinusoidal signal which is varying from 1 millivolt to 12 volt is applied at the input of a buck converter. These are the results of different cases. The plot A, C, and E are the harmonic response, and the bottom figure shows the harmonic distortion plots. The red color plot represents the analytical results, whereas the blue color plot denotes the simulation results. It is worth to note that there is a close resemblance between the analytical result and simulation results. The maximum mean percentage error in all the cases is 11%. Moreover, these harmonic expressions are useful to predict and model the power supply noise at the output of the PDN. As discussed earlier, that these fluctuations can affect the performance of both the analog as well as digital system. Therefore, we propose two methods for the analysis of SI matrices of an AMS system in the presence of deterministic supply noise sources. The first method is block approach indefinite admittance matrix. This is the graphical representation of a block approach indefinite admittance matrix. The steps of this BAIM are: the first is circuit model, then the generation of IM using the small signal model and its corresponding nodes, then elimination of terminals and simplifications, and reduction of the indefinite admittance matrices in the smaller matrices, and finally calculation of the circuit parameters using the two-port formulas. Based on the BAIM method, the formula for the gain, input impedance, and output impedance, phase, and overall gain in the presence of power supply noise can be derived by just an inspection of a circuit. Here, that YII and YOO are the self-admittance, YIO and YOI are the negatively signed mutual admittance parameters. Based on the gain, input and output impedance, a modified two-port model is developed. The modified two-port model of an N-port circuit can provide a quick analysis of the complete system in the presence of PSI. Several two-transistor-based circuits are analyzed using the inspection-based method and block approach indefinite admittance matrix method. Both the pre-layout and post-layout results are compared with the proposed analysis. The figure E shows the frequency response of a push-pull amplifier. The figure B shows the transient response of a push-pull amplifier, including all the possible noise sources. This figure C is the model error versus noise amplitude plot. The maximum error percentage for all the possible combination of noise sources is 7% when the noise amplitude is 20% of the VDD. These are the tables shows the comparison between the pre-layout and post-layout simulation with the proposed method. As seen, the maximum mean percent error is 2% for all the cases. The estimation by inspection method can also be applicable on the complex circuit, including the effects of interconnects, off-chip interconnects, packages, and deterministic supply noise sources. The steps for complex circuits are block level analysis, segmentation step, equivalent model of each block, inspection-based method, formation of single IM, and then finally overall response analysis. Now, the estimation by inspection method is extended to calculate the power supply indicator in the presence of deterministic supply noise sources. The power supply indicator can be calculated by dividing the supply to output response with the output transition, slope of the output transition at midpoint. Here, gamma is the represents slope, and V out is the supply to output response. This V out is calculated by estimation by inspection method, and gamma is derived by using a large signal analysis. The measurement results of a three-stage inverter are compared with the proposed inspection-based method for the PSIG calculation in terms of CPU time and percentage error. The proposed method is also compared with the sum of the existing method which are listed in this table. The intermediate stage PSIG can be calculated using the proposed method, which is not possible to analyze with the other existing method. By knowing the fact that PSI can itself affect the feedback path of a buck converter, therefore it can significantly affect the duty cycle and stability of the overall PD. Now, the harmonic duty of both the feedback as well as forward path are derived using the Volterra series and inspection-based method. These are the results of the closed-loop buck converter in presence of PSM. The proposed method is compared with SPICE simulation as well as harmonic balance method. And here the maximum mean percent error is 8%. So here this is the conclusion. In this presentation, I derived different distortion quantities of a PDN. Then two methods are developed for the analysis of power supply noise for N-port circuits. Then the power supply induced jitter is analyzed using the inspection-based method. The closed loop analysis of buck converter in the presence of PSM are derived. The proposed analysis using ultra series and inspection-based method has a significant speed up factor as compared to the other existing methods. Thank you.
Yeah, so thanks, Vijender, for this excellent presentation. So I have a couple of questions. First one is that when you are trying to analyze the PDN networks, right, in the pre-layout stage, there should be some input which goes to the layout, right, so that you can have a PDN aware layout, right? I want to know that what are those things you are trying to communicate to the layout. Okay, and when you have a large circuit, right, and you are doing the PDN analysis, okay, there are some techniques which actually partition the circuits and do a modular type of analysis of the PDN, right? And do you keep this scope in your research? That means have you tried to work with large circuits, right? And third, there are multi-VDD circuits at present, right? So how do you extend these methods for multi-VDD circuits? Yeah, that's all from my side.
Yeah. Can you please please again tell the first question? I can't hear your first question.
Okay, so first one is that when you are comparing the pre-layout and post-layout, right, in your pre-layout analysis, which you are trying to match with your post-layout results, right? So are you passing any information from your PDN analysis to the layout stage?
Okay, not for the layout stage. I'm not passing from the PDN. I am just keeping some fluctuations on the supply node. So that are the multi-frequency fluctuations. So I try to mimic the effects of PDN using the external source in that case. And
but what I mean to say that layout will have actually more extension in terms of interconnects, in terms of the multiple metallic layers and all these things, right? So it will be sort of more variations, right? So
yes.
So can you give some sort of input to the layout, right? So that so that your pre-layout PDN analysis helps to the layout.
Yes. What I did in the post layout and pre-layout, in the post layout I extract the RC parameters, RLC parameters, and then I feed in my closed loop expressions. So the technique is same for the pre-layout and post layout, and the main thing is the extraction of parameters. If the parameters are exact, then the my proposed method is gives accurate results. If there is some variation in the extraction of that small signal parameters, then it will might create some errors.
Okay, and the second question is that means how how you adapt with the large circuits.
Yeah, for the large circuits I use a block partitions approach. That is segmentation. So using first I develop a 2 transistor model circuit, and mostly the large circuit have a combination of 2 transistors. So either I replaced, if the circuit have more transistors, either I replaced by seeing there is the impedance from the particular node, and then I developed a program for that. If it's found a 2 transistors, then it will analyze using the estimation by inspection method. If from the netlist it can see that if there are more transistors, then it can replace that transistor by seeing.
No, when I tell large circuits, I tell that the circuit components which can have a different type of power requirements, right? So how your PDN analysis method works for those type of circuits?
So for different multi-power supply network, I need to analyze a separate PDN separately.
Yeah.
For separate cases.
Yeah.
And for the circuit cases, I apply the block approach, indefinite admittance method, estimation by inspection method by a block partitions approach. So partitioning the block, and then I apply the technique. And at the end, I merge all the circuits. And for PSIJ, the same technique, power supply inducers, I apply the same technique, that block partition and segmentation.
Okay, thank you.
And also for the measurement thing, I use the CD407 chip and use a chain of inverters to check and to validate my proposed technique. And for that, measuring the RC parameter, I use a Catley SES instrument. So I calculate manually calculate the capacitance and GM for the TD407 chip.
Yeah, okay, fine.
Hello?
Yeah, thanks.
There is a question from the audience. Is this method can be extended to high-speed circuits as well?
Yes, this I already applied for the high-speed circuits. High-speed means that if the frequency is in range of the power supply is in range of megahertz, and the input data is in gigabit, 1 Gbps. So for that, it's work for the high speed.
Okay, thanks, Vijendra, and thanks, Professor Amlan, for your questions. Then we'll move to the next presentation. The next presentation, the title of the presentation is Design Considerations for Robust Low Voltage CMOS Ring Oscillators. It will be presented by Lalit Dani from IIT Roorkee. Let's invite Lalit for the presentation.
Mondani. I am a scholar at IIT Roorkee. So my topic is design consideration for robust low voltage CMOS ring oscillators. So the main content is the RO oscillators that we are using in a lower near threshold voltage regime. So the challenges that we face when you are designing an RO at lower voltages, there are mainly three challenges. First one is on the architectural behalf, and second one is the performance models. Different performance models such as frequency models, tuning range, how to calculate tuning range, frequency, phase noise, and power estimation, and all design parameters. And the third one is the design methodologies. So in the design methodologies, we are using conventional design methodologies and how to overcome the challenges that we face. So for example, ROs, as we know, there is an inverter stage with n odd stages, and it is used for many different applications. And it is in anti-VGM, it is mainly used for IoTs, biomedical, and energy having systems. These are the performance parameters of an RO. The main challenges are there. There are mainly three challenges. The first one is that the conventional RO topologies are not suitable in near threshold voltage. So we propose new architectures that are very suitable and giving high performance as compared to the conventional ROs. The second one is that RO performance models. So we are using the nominal voltage performance models, and we find out that those models are inaccurate at lower voltages. This is because of the IV characteristic that changes from square law to near exponential current behavior. The third one is that the conventional RO design methodologies is very efficient because it is because we consider PVT variations at the later stage of the design after post layout simulations. So we need some parameters, some extracted parameters, so that we can use them at the earliest stage of time to predict the PVT variations, so that it becomes efficient and accurate. So the first challenge is that the RO topologies. So as we have seen, there are basically two RO topologies, differential VCOs and current starved VCOs. So the main disadvantage is that the series stack transistors are there, and also no rail-to-rail swing is there. Low oscillation frequency occurs, and small tuning range and high PVT variations. To overcome this, we propose new architectures. But we do that, we use an inverter stage, and in that, for tuning purpose, we are using MOS as vector for tuning the capacitance of the node. So what it will do that it will use in the inverter will be used to pull maximum current and pull down maximum current at the node, and this transistor will use to vary the capacitance, and from that we find out that the frequency varies linearly at lower voltages for these architectures, for bulk driven architectures. We have proposed in S3S. The second one, we propose the architectures. We propose in VLSI design. We propose new architecture that is very suitable at near threshold voltage. And these architectures, the DT-MOS type of MOS vector we have used different configuration for it. And the main advantage that it is giving very low phase noise, because it is pulling maximum current and pulling down maximum current at the oscillating node. So current is maximum here as compared to the differential ROs and current starved ROs. As you can see that the frequency varies, the tuning range is 0.6 to 2.36 gigahertz, and the phase noise is -90 and -95, and the very low power consumption and high FOM. The second challenge is the RO performance model. So performance model, the conventional performance models use this modeling that we assume that when the input reaches VDD by 2, the output starts to fall, and when the output reaches VDD by 2, the input reaches to VDD. And we are using saturation current for it. So what we assume at nominal voltage that the output starts to fall from VDD to VDD by 2, and we calculate the T fall from here, and the current we use is the saturation current. So but when we go at near threshold voltage, so this architecture, this delay model does not accurate because of the exponential current behavior, and output has just fall when the input reaches VSS VDD by 2, and overshoot and undershoot dominates, and threshold points varies with PVT variations. So because of this. Also, in the conventional, we use inverter stage as an RC circuit. Also, we use sinusoidal oscillating node voltage. So these also decreases the accuracy of a delay model. To overcome this, we propose new threshold points, or transition threshold points. What we find that when we for a RO, for a single stage RO, and the for input for transitions, for example, for a falling transition, what we found out that when it reaches a maximum overshoot value, the current starts to rise linearly, and when it reaches, when V input is equal to V out, the current saturates. So it's not that we assume only saturation current. Here we have to divided the current as per its device operation, and we calculate the delay. So we divided the total delay of an RO stage into 4 parts, and divide the current as per its behavior. So the 4 TTPs are when V in equal to V out, and the V in equal to V out, and maximum undershoot and maximum overshoot. So what is the advantage of these TTPs? So the main advantage is that it's very linearly with the design parameters. As you can see here, with sizing, VDD, and temperature at different, with supply, temperature, and different process corners, it varies linearly, these TTPs. So we can use the TTPs, we can model it, we can use it as a lookup table model, we can calculate the sensitivity of each parameter from one-time simulation, and we can use them to calculate the PVT variations at the early stage of the design. So we use it for inverter chain and buffers, these TTPs. Then we use it for ring oscillators. We are getting accurate delay and frequency and tuning range. Then we apply it for FinFET technology also, and we are getting the same device operation of the current for a RO stage at lower voltages. The third challenge is the RO design methodology. So as we can see that the previous design methodology, it considers the variation, the PVT variations at the later stage. So if the variation is not within designer's limit, so resizing we have to done again, and that we are using again for. So we have to do it again. We have to start from the scratch. To overcome this, what we have proposed LUT-based design methodology, in which we will use those TTPs values and with PVT variations, and we embedded in the model, and from that we can calculate the design parameter that is PVT aware as per designer specifications. And so this example, so we apply it to calculate the PVT, the maximum change in the tuning range, maximum change in the frequency with different PVT variations. And the proposed architecture VBROs, we propose new delay models for VBRO. So for that we calculate capacitance model for MOS vectors. In that the capacitance varies with from weak inversion to depletion region. So we take this point as a parameter which varies with the control voltage, and calculate the capacitance. So same has been done for bulk driven MOS vectors. In that this point is very linearly. So we embedded these points, vector points, in our proposed models TTPs, and we also calculate the capacitance at different transitions, and we calculate total delay, and we find accurate delay. And the accuracy of these models are up to 96 to 98%, and it is very efficient. In less than 5 seconds, for example, we calculate the PVT aware PVT design methodology, PVT where VBROs are design parameters. The summary is that we propose new architectures. We propose new performance models using TTPs, which are extracted as per device operation. And third one is that we have proposed new design methodology, which is PVT variation aware, and we are using it at the early stage of design to make it more efficient. Thank you.
Yeah, thank you, thank you, Lalit, actually, for the nice talk. So I have so one or two simple, curiosity about your approach. So, how do you validate this? So, you have find out good models for finding out this robust low voltage ring oscillator design considerations. So, have you ever tried to fabricate them or in some other manner, integrate with an existing system and see the accuracy of your modeling? So this is my first question, and second is some of the nice architectures you have given for the ring oscillators. So what are the impact on area over it compared to traditional normal ones? So these are the two questions from my side.
Thank you, sir. The first question that you have asked, that yes, we have embedded this. We verified our model through post layout simulations at different technologies, and also we have using FinFET technology. We have and TCAD tools. We have verified our model, and as per our model, we find out that these TTPs that we have proposed, these are very sensitive to these the models, the points that we want to use while giving a delay model or any performance model for an RO. So we have verified it with TCAD simulations and post layout simulation. We have verified, and also we have put it in PLLs. Phase lock loop we have put, and from that we find out that our model is working with great accuracy and efficiency. And just about the second question that you had asked, yes, we have implemented these vector-based ROs in PLL phase lock loop, and the second one, regarding the sizing. So at lower voltages, what we need maximum current at the oscillating node. So in the conventional architectures, for example, current stopped RO. So we use the MOSFETs for tuning. We are generally varying the resistance of a transistor. So to put maximum current at the oscillating node, we are increasing the width and length of that particular transistor, so that maximum current to be pulled up and pulled down at the oscillating node. But here in our case, we easily generate high current at the oscillating node by using very small transistors. So means the width and length, the sizing is very small, and as compared to the current stopped ROs for the same performance, it is the size is the area is less for the conventional as compared to the conventional ROs. BBR.
So I think let us thank from Lalit from my side. In the interest of time, we cannot extend the question answers. Thank you once again.
Thanks, Lalit, for your presentation, and thanks, Professor Santosh, for the questions. Is there any questions from audience? No questions from audience. Thanks all the presenter, and thanks all the judges for their time and for nice presentation. And with these all, today's session is all over with 6 presentations. Tomorrow we'll come with another 6 presentations for this SRF. With this, I'll conclude the session. Okay, thank you.
Thank you.
Thank you. Thank you all. Thank you.
Thank you all.
Yeah, thank you.